can, just so everybody can have this and have some answers. So let me zoom in here. All right, I'm going to work on balancing these. I can also do some work as far as classifying them. This is combustion reaction. We know it's combustion reaction because it has oxygen, it has water, and it has carbon dioxide. When we go to balancing, we always want to start with the most complex as a general strategy, and we put those lines in which are already here. At this point, I see my inventory, I will have 6 carbons and 6 hydrogens. If I decide to put a 6 here, that would take care of the carbons, but my oxygens would change. Let me see if I can put a 3 right here to take care of the hydrogens. So hopefully you can see that there are 6 carbons on each side. There are also 6 hydrogens. The number of oxygens, though, is it's an odd number. So 3 times 1, there's 3 of them here, but then 6 times 2, which means 12. The only way that I can get 15, because you add those 2 together, oxygens over here is if I had a 7.5 times 2. When you see that, you can immediately go through and double everything. So you instead make this a 15, this would be a 2, this would become a 6, and this would become a 12. So your coefficients should be 2, 15, 6, and 12. Please note that half is the way that you can know or be aware of just doubling everything to get whole numbers. Okay, let's look at the next one. Next one is sodium iodide, lead sulfate, and lead iodide and sodium sulfate. Notice that the sulfate is on both sides. This side has 1, 2 sulfates, and this one only has 1. I'm going to go ahead and start with the lead iodide, though, because I'm going to say that it has 4 parts. I would put a 4 here in order to make the iodides 4. Right now, the lead is 1 on this side and also 1 on this side. Sulfates are 2 and 1. So maybe I'll put a 2 here. That changes my sodiums to 4 and my sulfates to 2. And my lead is still balanced and my iodides are balanced. Actually, everything is balanced now if you take a careful look. 1 and 1. We don't typically write the ones, but I just put them in there to help you get this. Okay, next one, ammonia plus oxygen goes to nitrogen monoxide and water. Okay, I think we have a classic, what I like to call a 3-2 problem, meaning we have, 2 hydrogens and 3 on this side. Almost always you can help solve the problem by putting a 2 here and a 3 there. That takes care of making that 6 hydrogens. Now let's look at what happens to the nitrogens and the oxygens. So I have 2 oxygens over here on this side, and I have 2 oxygens. On this side, I have 3 oxygens and 1 more. Okay, so that's 4 oxygens. The only way I can get 2 oxygens there to get to 4 is to put a 2 here, but my nitrogens are 2. So why don't I take care of nitrogens first? When I do this, this NO becomes doubled, so I have 2 nitrogens and 2 oxygens, but I also have 3 more here, so I have 5, and over here, the only way I can get to 5 oxygens is if I multiply by 2.5. Hopefully you immediately are starting to think of our first problem. If that is a decimal 0.5, you can double this to 5, but if you double that, you got to double this one, you got to double this one, and you also have to double this one. All right, let's keep cooking. Iron oxide, iron hydroxide and iron oxide and water. This would be a decomposition. I'm sorry I didn't say anything about this one. This would actually be double switch. Yep, double switch. This would be also a double. Okay, so we've got 2 irons over here, and we got only 1 there. Let's just take care and solve that. So if we put a 2 here, the irons are good. At this point, we would have 2 of these, so that would be 3, 4, 6 oxygens, because of the 3 and the 2, and then there would also be 6 hydrogens. All right, so if we put a